Hi everyone, I'm Jeremiah Semplis, and welcome to my second video reflection for CMSC 341. In the first half of this course, we built the foundation, SQL, queries, relational basics. In modules 5 through 9, the course shifts from working with data to designing it, managing it, and understanding the entire database industry around it. I want to take you on a single journey today, the journey of data itself. We'll start with one messy spreadsheet and clean it up through normalization. We'll connect related pieces with relationships. We'll see how a database and a database management system keeps everything safe, fast, and consistent. We'll meet the people who do this for a living, and we'll finish in the cloud, looking at where the industry is headed as well. Let's get this started. So here you have your normalization, your relationships, your database management system processes, your careers, and your trends. That's what we're going to be talking about, and that's what the book talks about as well. So in module 5, this is all about normalization, the process of cleaning up redundant data and fixing what the textbook calls modification anomalies. Imagine one giant table, okay? You have students, professors, departments, and majors all jammed up together. Like the faculty example from the slides, there's three things that can go wrong. An insertion anomaly. You can't add a new professor until at least one student is assigned. Your update anomaly, which means changing one professor's department means updating dozens of duplicate rows. And then your deletion anomaly. Removing a student accidentally erases the only record of their advisor. Normalization fixes this through progressive normal forms. First normal form says every field must hold a single atomic value, no repeating groups. Second normal form requires every non-key field to depend on the entire primary key, not just part of it. Third normal form removes transitive dependencies, where one non-key field secretly determines another. The big idea here is by splitting one large table into multiple smaller related tables, redundancy disappears, and the data becomes trustworthy. Most production database live in third normal form. That clean structure is the foundation everything else in this course builds on. And here I have the visualization. You have first normal form, second normal form, third normal form, and the goal is to reduce redundancy, improve integrity. Each step solves a different kind. Now, Module 6. Once tables are normalized, Module 6 is where they become a true database. This module is about relationships and design. A database designer works with business analysts to capture the rules of the organization, then translates these rules into entities and relationships. This is called information and relationships. Entities and relationships. This is called the information level design, and it's independent of any specific database management system. It's the logical blueprint. Two notations are common: database design language, or DBDL, which is a text based and it labels primary keys as PK, alternative keys as AK, secondary keys as SK, and foreign keys as FK. Now you have your ER diagrams where you connect two tables. This one we used here would be a crow's foot notation, marking the many side and the one side. And now you have different types. For one, you have a many to many, which needs a junction table. Relational databases can't store MN directly. You split it in two. So you have your students here, that's one. Your declared majors, that's many. Declared majors, that's many. Into majors, that's many. Three types matter: one to many to many. And here's the catch: relational databases can't physically implement a many to many. You have to insert a junction table that splits it into two one to many relationships, as shown. Two more concepts close out the module. Referential integrity prevents orphan records on the many side. Cardinality describes how unique values are within a field. Primary keys have high cardinality. Foreign keys have low. Get these right and your database is curable, consistent, and ready for users. Now, Module 7. This is the first part we have to talk about, which is CRUD. Create, read, update, and delete. Second is the catalog, which is your metadata about the database, basically the data about the data. Third, concurrency, many users, no conflict. In a way, think of it like this: enterprise systems prevent dirty reads, non repeatable reads, and phantom reads using ACID properties, aka atomicity, means a transaction is all or nothing. Consistency keeps data in valid states. Isolation controls when others see your changes. Durability guarantees committed transactions survive crashes. Fourth, recovery, backup, journal, rollback. There are two flavors. Forward recovery rebuilds a lost database from a backup, then replays the after images of committed transactions. Backward recovery, a rollback, undoes problems, transactions using the before images stored in the journal log. Fifth, security, encryption, authentication, privileges. These are really important if you want to protect your database. Encryption scrambles data in transit authentication, verifies who you are, and authorization controls what you can do. Using SQL keywords like select, insert, update, and delete. Now, six, integrity, data integrity, constraints and validation, primary keys, foreign keys, validation rules. Seventh, data independence. Schemas changes don't break apps. So you have data independence. You're changing the database structure without breaking every program. Copies across distributed locations, modern tools like Git apply the same idea to the source code. Lastly, you have your replication, synced copies across locations. These eight services are what a real database management system from a folder separates it from a folder of a spreadsheet. And here's your acid, atomicity, right? All or nothing, either the entire transaction completes or none of it does. Consistency, that only changes in valid, predetermined ways. Constraints are never violated. Isolation, others users don't see partial updates. Transactions appear sequentially. Durability, once committed, the changes survive, even if the crashes can't undo it. The rules, every transaction, these are the rules that every transaction must follow. Now, Module 8. Module 8 turns from technology to the people who do the work. The classic role is the database administrator, the DBA. The DBA reports to the CIO in a large organization and owns organizing, managing, and securing the database. According to the Bureau of Labor Statistics, the median annual salary in the figure cited in this module was around $90,000 and has a projected job growth of 9%, which is faster than the average. The database's duty cover policy, granting access privileges with SQL grant and revoke, enforcing security, planning backups, writing the disaster recovery plan, in which that plan defines a recovery time objective, how long you can be down, and a recovery point objective, how much data you can afford to lose. It it inventories assets, uses RAID storage and uninterruptible power supplies, and gets tested against realistic scenarios. DBAs also handle technical functions: design, testing in a sandbox, performance tuning, and maintenance. Sometimes they even denormalize a table, accepting redundancy on purpose to squeeze out more speed. Around a DBA is a career ecosystem: application DBAs, system DBAs, performance analysts, database architects, data modelers, and increasing the analytics role. Increasingly, the analytics role, I meant. Data analysts and data scientists who turn raw data into business insight using tools like Tableau and Power BI make the entire database scheme change. Certifications from Oracle, Microsoft, and IBM map onto every step of this path. Module 9 looks at where the industry is headed. Architectures have evolved dramatically. The 1960s mainframe era gave way to client server in the 80s and 90s, splitting work between fat clients and thin clients. Then came three tier and n tier architectures, separating presentations, application logic, and the database into independent layers at scale. Today, cloud computing begins with bringing centralized architecture back, but in a new form. AWS, Azure, and Google Cloud use virtualization to deliver shared, scalable infrastructure as a service. Data warehouse stores subject oriented, integrated, time variant, non volatile snapshots optimized for analysis. OLAP or OALAP. Online analytical processing organizes that data into multi-dimensional cubes. You can slice, dice, drill down, and roll up. Distributed databases push data across many sites with location, fragmentation, and replication transparency. Then there's NoSQL, document, graph, key value, and wide column stores, built for messy, web-scale data. Object-oriented databases handle complex data like CAD drawings and geographic information. And then there's big data, characterized by the three V's: volume, variety, and velocity. Hadoop on the cloud handles enterprise-scale workloads, while small businesses can dip in through Google Analytics. Data formats have evolved too, from ASCII to CSV to XML to JSON, the lightweight, self-describing language of modern web APIs. Here you can see the NoSQL and big data. When data is too messy, too varied, or too fast for SQL alone. And that's what we talked about, which is you document, which is the web app data, MongoDB, graph recommendations, social graphs, key value, cache, simple lookups, wide column, your many column analyticals, and then you have your three V's here: volume, massive amounts of data from many sources; variety, text, images, videos, sound, behavioral signals; velocity, created and consumed at incredible speed. So database design isn't just a technical exercise. It protects integrity, supports decision making, and scales with the business. And that's the journey, from raw, anonymously riddled data through normalization relationships into a fully managed database management system supported by skilled people and pushing it into the big cloud, the big data, and the beyond. My biggest takeaway from these five modules is this: database design isn't just a technical exercise, it's a discipline that protects integrity, supports decision making, and scales with the business. Every concept we covered, atomic values, asset properties, OLAP cubes, JSON, exists because someone needed reliable answers from messy reality. Whether I end up as a DBA, a data analyst, or just a developer who writes good queries, the principle in CMSC 341 will travel with me. Thanks for watching, and I'd love to hear your feedback.